Alright, here we are in example 9.3. And essentially what we want to do with 9.3 is back in example 9.1, we created a rate function to solve numerically for the velocity of a projectile, a falling object, as a function of time. And so what we want to do now is just kind of build upon that solution and create a function to give us something that looks more like a numerical solution. And so what I mean by that is to create a function where if I specify time, it returns the velocity of my object at that time. So again, looking more like a numerical solution where if I want to solve for v as a function of t, right, I just specify t, or pass value of t, and it returns velocity. And then also once we have that, see how we can use that with f0. And so we're given an example of at what time is our velocity equal to 15 meters per second. Okay. So let's go back over to MATLAB and let's play with it. Okay. Oops, so that's my tank drain. I didn't close it up, so I'm going to clear my variables and clean my space. And then free fall rate is this guy here. Okay, so let's play with free fall rate. Okay. And the first thing I'm going to do is I'm just going to solve the our differential equation again and look at exactly what we have. Okay. So if I want to solve this differential equation, okay, and assign the results to variables, I would do, say, t comma v is equal to ODE 45. I'm going to give it a function handle for my rate function. So at free fall rate, a time range, so say 0 to 20 seconds, and then initial condition, initial value of v, which is 0. Okay. All right, and so before I press return and we look at things, remember when trying to understand ODE 45, think about Euler. Okay, so what MATLAB's going to do is, notice our initial condition here, our value of v is at time equals 0, which is the first entry in this time vector, right? This time range vector. So what MATLAB will do is it'll take my initial time and corresponding velocity, pass that to my rate function, use that to evaluate the rate of change of v with respect to time at time equals 0, and use that to move my system forward in time. Okay, it'll keep doing that until I get to a time that's equal to the final time in my t range, at which point it'll stop. Okay, so if I press return and I were to display t, okay, the first element in my time vector, t, is 0. The final element is 20. Right? So t1 is 0. T end is 20, the time I integrated to. Likewise, if I look at v, okay, v is going to begin at a velocity at time equals 0. Okay, and then remember, all these elements of v are equal to the value of my function at corresponding elements of t, my time vector. All right, so v of 20 actually corresponds to the velocity at, I take that back. V of end, my final velocity, corresponds to my final time, which is 20 seconds. Cool. Okay, so to get this to look more like an analytic solution, what I could do is I'm going to save this as, maybe call it free fall fun. Okay, I'm going to create a top function. Okay, and free fall fun, it's going to have an input of t for time. Okay, and then what I would like it to do, and actually, we can do this a number of ways, but what I'd like to do is let's solve our differential equation just like we did in the command window. To be ODE 45. Okay, at free fall rate. Okay, and what I'm going to do now for this time range is I'll start at 0. Okay, but then my final time is going to be t. Right, so maybe let me call this t final. T final. Okay, integrate from 0 to t final, and initial velocity is 0. Okay, cool. Then what I want to return is y end. Okay. And actually, let me call this v to be consistent with before. So we're all on the same page. Okay. So I created a top function. Okay, and all the top function does is solve my differential equation with the rate function, where the rate function is a helper, from 0 to t final, where t final is a value that's provided by or passed from the command window with an initial velocity of 0. Okay, I solve, store the results to t and v, and then what I return is the final element of v. And why I'm returning the final element of v is that'll be the velocity at t final, which is the time that's provided by the user. Okay, so if I want to solve for the velocity at 20 seconds, then I can call freefall fun and pass to it a time of 20 seconds. All right, and I get 19.6191. Right, so something that looks very similar to a function. So when I solve this animal analytically, what I get is an expression for v as a function of time. Here, I've essentially just created that with my numerical solution. All right, cool. So far, so good. Excellent. All right, I could even go as far as to plot this animal if I wanted to. So if I were to do fplot, right, because this is now a function with a single input, I provide it with the value of t, it's going to return my velocity at t. So I can do an fplot at free fall fun. Now let's go from 0 to 20 seconds. So yeah, comma, 0 to 20 seconds. And I can do, say, black lines. Right. Cool. Oh. It's actually, it doesn't like it. Reason it doesn't like it is because it wants my function to be, vectorized as 1 is what's complaining, but 2 is my time needs to be greater than 0. Okay, so we'll come back to this in a second. Okay, so I can use fplot even to plot velocity as a function of time. Okay, cool. Okay, so this is nothing more than a function that takes as an input of time and returns the velocity. Right, so I can use it with things like fplot because it doesn't care what happens inside. All it cares is that it passes a single variable to it and it returns back a single variable. Okay, so now in terms of all these warning messages, the issue is it would prefer a function that's vectorized. And unfortunately, in this case, we can't vectorize our function because each one's a unique call to ODE45. So you would just have to take that warning if you want to use fplot. But up here, it didn't even work, right? And so the issue is I gave it a time range of 0 to 20. And so it would start by trying to evaluate my function at a time of 0. And that's not going to work. That's going to give you an ODE45 error message because the value of 0 would mean integrate from 0 to 0. The area is empty, it's going to fail. Okay, so cool. All right, so normally I wouldn't, use fplot with that, but it's just an example of, now we've created this black box, right? We've created, a function where I pass to a t and it returns velocity. Okay. The other thing this will allow us to do is we could combine this with f0, right? We could do it in a number of ways. One would be, okay, so free fall, actually, let me put that plot back up. All right, so free fall, we start with the velocity of 0, then velocity increases until it reaches a constant value. Okay. If we want to solve for when the velocity is equal to a specific value, we can use f0. Okay, but remember, f0 is looking for zeros. And so in this example problem, okay, if I want to solve from the velocity is equal to 15, what I'm going to do is take the velocity and subtract 15 from it. I'm essentially going to shift things down. That way, what f0 is going to try and search for is for the time that I could pass to this function such that it returns a value of 0. It'll return 0 when v is equal to 15. Okay, We could do this via an anonymous function, and we can look at that example in a second. And then by shifting it to, we'll satisfy the requirements of the intermediate value theorem, where initially, where we start with a velocity of 0, it'll now start at value of negative 15. This will return, and then it'll become positive because the terminal velocity is greater than that. Okay, so now with this, I can use f0. Okay, so if I want to solve for when the velocity is 15 seconds, we can do f0 at free fall fun. And then we either need to give it a time, or in this case, a time range to search over, where the lower bound has to be greater than 0. For the same issue we saw with fplot, if I pass a value of 0, it's going to try and integrate from 0 to 0, and that's not going to work. Or an initial guess. So I could give, say, an initial guess we can try of 10 seconds and solve, and we get a very precise answer of 2.8923. Okay. And so again, in terms of potential errors, if I were to search from 0 to 10, I'm going to get an error message, right? And the error message is my lower bound starts with 0, and it's going to try and call ODE 45 with the value of integrating from 0 to 0. So that lower bound just needs to be greater than 0. So you can do 0.1. I could do 1 e to the negative 6. Right? It's still greater than 0. It'll work. All right? Cool. Okay. And just to confirm that this is right. Okay. So let's go ahead and let's solve our differential equation. Put this point up there and make sure it looks right. Okay. Just in the interest of doing it. Okay. So if I want to solve my differential equation, it'd be ODE 45 at free fall rate, right? So let free fall rate in here. Let's integrate from 0 to, we can just do 10 seconds. All right, let's go to 20. Let's go out to the terminal, 0 to 20, with an initial velocity of 0. Okay, so I'm going to do a hold on, so plot multiple data points. Okay, and I want to plot t comma v, and let's do that this time as a black line. Cool. All right, so here's my trajectory. Okay, I want to solve for the time it takes to have a velocity of 15 meters per second. So let's plot a horizontal line corresponding to 15 meters per second. So our x values, we want to go from 0 to 20, and our y values in both cases will be 15. All right, we'll use that to plot a horizontal line, and we'll make it a red line. Okay, so remember this is x vector, y vector. X vector is 0 and 20. We want to go from x-axis range from 0 to 20. And in both cases, we want our y value to be 15. All right, so the effect is a horizontal line. Okay, cool. Okay, and so we want to solve for this time. We just did. It's this. So let's plot that as a vertical line and see if we get a perfect cross at our curve. So x value now will be sol in both cases. Then our y value would be, okay, that goes from 0 to 20. And we'll plot that as another red line. Okay. So x value is going to be our solution. And then our y values, we want to go from 0 to 20. Okay. Hey, and x marks a spot. Perfect. All right, so we just solved for, oh, yeah, and just keep going. Sol, comma, we're solving for when it's 15. Red x. All right. X marks the spot. We got it. Okay. Cool. All right. So that's example 9.3. Okay. If you want to have some extra parameters, we could do that as well. One way even to do it would be not to have that 15 there, but instead to use an anonymous function. So maybe free fall. I'm going to solve for the height's 15. Okay, now this is just returning velocity. Well, I could put an end to that. I can make it free fall fun at t minus 15. Okay, so then f0 rather than free fall fun, I could use our anonymous function free fall 15. Cool. Okay, and then if I wanted to know when it was, I don't know, 10 meters per second, I could just create a new anonymous function where all I'd have to do is subtract 10 instead of 15 from what this is returning, which is v. And just resolve using that new error function. All right, cool, got it. All right, so now we can set up a function where I pass t and it returns velocity. We could also, just as well specify velocity and solve for t now. All right, so we can do everything you can essentially with an analytic solution, but solving numerically. Right, and personally, I think this is a beautiful thing. When I took differential equations, yeah, we can separate and integrate, some nice simple first-order differential equations, well, even second order and higher. But eventually, they get more complicated, and it's a matter of remembering general solutions, which I can't always remember. But using this nice compact code, I don't have to solve it analytically.